Alright, today we're going to talk about waves and sound. I like the sound of that. So here we go. Alright, basically anytime an object moves periodically, okay, periodically is when it moves in a direction where it repeats, okay. It could be a pendulum going back and forth, side to side, vibration. It could be swinging side to side, then going up and down. We normally tend to say that it vibrates, or another word for vibrate is oscillates. Okay, and it has harmonic motion. Okay, so harmonic motion is just anything that has a periodic or repeating motion, back and forth, side to side, up and down, and so forth. Okay, now if the vibration carries energy from one place to another, it is called a wave. All right, and so waves are basically just movements of particles or molecules that carry energy from one place to another. Now, there are several different kinds of waves. We're going to look at this type of wave first because it's the most common. People think of this as a transverse wave, okay? But we'll talk more about what that means in a minute. But let's just talk about some of the parts of a wave, all right? Now, in this case, they have a ball and a spring, and they're bouncing it. It's going up and down, up and down. And if you thought about this as tracing paper here and put a little marker on this and ran the paper through, as it goes up and down, it would trace this path. This describes the path, this time going this direction, what happens to the movement or the vibration of the ball on the spring. Okay. Now, if you did not stretch out the spring, this would be its resting position, or where it would normally hang from the spring. Okay, then it's been stretched down here, and then you let go of it, and it goes up and down like this. All right, so this starting spot right here is called the resting position. All right, so this is your resting position. All right, now how high it goes above that, or how high it goes below that. This part here could also be labeled the amplitude. Okay, in other words, the maximum distance or displacement from its resting position, or its equilibrium. Equilibrium is when everything's balanced, it's not moving. That would be the same as resting position. So how far, what's the most farthest distance it gets from that? And that would be right here on top. It would be right here on bottom, right here on top. Anywhere from the resting place to the top, or from the resting place to the bottom of each wavelength would be the amplitude. All right. The wavelength is the distance between any two identical parts on two waves. All right. So from this spot here to this part here would be one wavelength. Why is the wavelength not here, even though it's even with that one? Because this one's going up, that one's going down, this one's going back up. So this is when it first repeats that location. Even though it goes through that location here, it's going down. That's not the same as here, so it doesn't count until it goes back up. A lot of times we move wavelength from the top of one wave to the next. Okay, but it could also be from the trough or bottom of a wavelength to the next trough, or it could be anywhere along the wave to the next place on this the second wave, doing the same exact place, going up or going down. Everything has to be exactly the same. All right. Now, having to do with wavelength affects what we call the frequency. Okay, let me just give some examples here off to the side. See if I can draw these nice and neatly. Okay, the frequency is how many of these waves or vibrations go by per second, or however often you want it to be. Okay, and so let's just say both of these represent 1 second as this wave goes, and this is how many wavelengths go by. Which of these would have the highest frequency? Well, this one has 1, 2, 3, 4 wavelengths. 1, 2, 3, 4, 5, 6, 7. So this one has almost twice the frequency of that one. Okay, so frequency is just the number of vibrations or oscillations that an object makes in a given time. Okay, and so this one does a lot more in 1 second than this one up here does. So we would say it has a higher frequency. We say this one has a lower frequency because it does not change very much. Now the time can be different things, but usually it's a second. Okay. When it is in seconds, we say that the frequency is measured in hertz. Okay, H-E-R-T-Z, or the abbreviation of it would just be H-Z. Okay, so hertz. So we're talking about how many hertz it's going. We're talking about how many vibrations or cycles, wavelengths, whatever you want to think about it as, per second go by. Okay, in 1 second. All right, so that's what a hertz is. Now, Just for example, we have AM radio station, all right, AM station, and we have FM stations. Now, if you look on the AM dial, you could very well have a number like 1180, okay, as a radio station. If you look on FM station, you might have something like 99. Hang on here, we got an issue here. 99.5, or maybe even 101.5. Okay, and someone says, well, which one of these has a greater frequency? Well, if you just look at the numbers, you'd say, oh, well, the AM is bigger numbers, and AM is bigger numbers, but AM is measured in kilohertz, which would be thousands of hertz, whereas FM is measured in megahertz. Occasionally they'll give their frequency that they broadcast at, and that's basically what this number means. Okay, 99.5 means that there's 99.5 mega or millions of hertz per second. Think about that. In 1 second, 99 million of these little wavelengths would go by. There's a lot of wavelengths going by in the air right now. AM, on the other hand, even though it's 1,000 and something, that would be 1,000 would be a million. So this would really be, if you put these on the same megahertz scale, this would be 1.18 megahertz. Okay, whereas FM is way down toward 180, 89 to 100 megahertz. This would only be, this is a very high number for AM, and it would just be 1.18 megahertz. Okay, so it'd be very small. And so AM has a lower frequency, even though the numbers are bigger on it. Okay, because it's measured in kilohertz. Now, cell phones, on the other hand, operate on the gigahertz scale. Okay, so that would be billions of vibrations or wavelengths per second going by. So they're even higher than AM or FM radio. Okay, now the other thing about a wave we need to know, we've talked about frequency, we've talked about amplitude and wavelength, is the period of a wave. A period, once again, is something that repeats, okay? And so the period is the time it takes to make one wavelength or one complete vibration. If this goes up and down and back, how long did it take for it to do one? Okay, and basically the period and the frequency have what we call an inverse relationship. Okay, so the frequency is equal to 1 divided by the period. Okay, whereas the period is equal to 1 divided by the frequency. So if one is large, the other one is going to be very small. So for example, let's just say I have a toothbrush and it makes 90 vibrations back and forth on my teeth per second. So the frequency of that would be 90 hertz, because how many vibrations does it make per second? Okay. Now the period, meaning how long does that take, would be 1 over 90, which is going to be about 1 point something, well, 0.01 something seconds. Okay, it can be a very small amount of time. So the bigger the frequency, the smaller the period. The lower the frequency, the bigger the period. Okay, they're going to be inverse of each other. When a wave moves through something, the something it moves through is considered the medium. Okay, the medium in this case, say we're talking about sound, it's traveling from my mouth, my vocal cords, and it vibrates air, and those air vibrations pass out until they hit your ear, and then you pick up those vibrations on your eardrum, which translates it to what your brain hears as sound. Your brain interprets that as sounds. Now, the medium that the sound waves would be moving through would be the air. Now, when I speak and it moves through the air, notice the air molecules do not move. You don't feel wind, you don't feel the air molecules moving, but you feel the vibration of them. Once my voice has gone through the air molecules, okay, when it hits them, they start vibrating. Once it goes past them, they quit vibrating, and they're still basically where they were. So in other words, when we talk about the speed of a wave, we're not talking about the medium, the air, for example, in this case of a sound wave, moving, how fast it's moving. We're talking about how fast does the energy move through the air, from one part of the air to the next part of the air. Okay, so it's the energy that's moving, not the medium. So for example, when you speak, generally speaking, sound moves. It varies a little bit, but basically at about 340 meters per second. Okay, so very quickly. In other words, that's about a little over a football field per second. So sound moves relatively quickly, not as fast as light and some other things, but very, very quickly compared to speeds that we can do or conceive of. Now, one last thing that's important to get is that the frequency of the wave is not the same as the speed. Okay, it's very easy to get this confused because we think, oh, this one has a high frequency, so it must be moving faster than this one. These could be moving at exactly the same speed. It's just that this one has more vibration as it's moving. So the vibrations are up and down, so to speak, and the speed is how fast it's traveling through the air or through whatever to get to wherever it's going. And so if this is at 1 second, they are passing the same distance, then they are of the same speed. But we'd say that this one has a much higher frequency, but they have exactly the same speed. All right. Now, so if we talk about a speed of a wave, we learned earlier that speed is equal to the distance that it travels divided by time. Okay, so if we were to answer that for a wave, we know the speed is equal to the distance it travels is the wavelength. Sorry about that, not looking very good, but the wavelength. Okay, and so it's going to be the wavelength divided by time, which has to do with the period. Okay, but if we replace the period with 1 over frequency, basically the bottom line is that the formula for wave speed changes into so the wave speed is equal to the frequency of the wave times the wavelength of the wave. All right. So to go back to our example of earlier, if we had these two waves and they have the same speed, then that means the one that has the higher frequency, which is these, would also, in order for it still to equal the same speed, would have to have a shorter wavelength. Okay, so a bigger frequency times a shorter wavelength will give you the same speed as this one, which has a lower frequency, but it has a longer wavelength. Therefore, that's going to give you equal amounts, equal speed. In order for them to go equal speed, if one has a greater frequency, it has to have shorter wavelength and vice versa. If we take just the example of this first one and say, okay, we're going to increase the wavelength, but it's going to have the same frequency or the same number that come by per second. So in 1 second, for it to have a greater speed, it has to have a greater wavelength. It could still have the same frequency, 1, 2, 3, 4, but it has to have a longer wavelength. Okay, and therefore it would have a higher wave speed if it went this far in 1 second. All right, for the next section, we're going to talk about the two types of waves. We already talked about transverse waves that go up and down. We're also going to talk about compressional waves get squeezed together, like an accordion, then spread out, squeeze together, spread out. Okay, but we'll talk more about that the next one, since we'll only have about 25 seconds, and I don't think we'll have time. So we'll see you on the next one.